Hello and welcome. In this video, I want to take a look at Green's theorem. Now, Green's theorem is an extension into two dimensions of what we call the fundamental theorem of calculus. And I guess it's also an extension of the fundamental theorem of line integrals. So remember what these are, right? That if you have the integral from a to b of f prime of x dx, that's f of b minus f of a. Now, it's not written like this every time. In fact, several textbooks I've seen, if it's written this way, they call it the net change theorem, as opposed to the fundamental theorem, but it's the same thing. That if you're integrating a function, you've got to find its antiderivative, plug in the two endpoints, and subtract. Okay, well, if you already have that function written as the derivative of something else, it's pretty easy to find the antiderivative, right? Likewise, with the fundamental theorem of line integrals, if you have the line integral of the gradient dr, then that's just equal to f at the endpoint minus f at the start point, okay, where the curve is parameterized by r with t between a and b, right? So that was the endpoint and the start point. So notice in each of these, you're integrating essentially a derivative, right? That the integral of the derivative is just what happens to the function at the endpoints subtracted. Likewise down here, this gradient isn't a derivative, but it very much acts like the derivative, right? That when you're doing optimization problems in Calc 1, you know, where are the high points and where are the low points? Well, there are places where the derivative was equal to 0. So you took a derivative set equal to 0, solve for x. When you're doing optimization problems in Calc 3 and you want to find high points and low points, well, where do they happen? Well, they happen where the gradient is equal to 0. And so you set the gradient equals 0, solve for x and y and whatnot. So that the gradient of a multivariable function behaves in a very similar way that the derivative behaves for a single variable function. Okay, and the fundamental theorem of line integrals is essentially saying if you're integrating this derivative, this gradient, along a curve, then what you need to do is you need to find out what the potential function is, essentially the antiderivative, right? I say down here, both integrals depend on the antiderivative. I mean, we call it an antiderivative up here, we call it a potential function down here. So you find that function, see what happens at each of the two endpoints, and subtract. Now, it may not be immediately obvious what the significance of those endpoints are, but really what they are is the boundary of the interval or the curve that you're integrating over, right? In Calc 2, when you're integrating, did I say Calc 1? It's Calc 2, right? When you're integrating this function over the interval from a to b, there's a whole, piece of the x-axis that you're integrating over, and the endpoints are the boundary between the interval that you want and all the stuff you don't want, right? So that's the boundary. Likewise, R of B and R of A are the endpoints of the curve. I don't know if this is 2D or 3D, but you're integrating along a curve, and you have the start point and the end point. Now that curve may continue on, but you're only looking at a particular piece of it. And RA and RB are the two endpoints. They're the part that divides the curve into the part you're integrating over and the part that you're not interested in, right? So essentially we're saying we can tell you about the integral of the derivative of a function by knowing what happens to the potential function, or the antiderivative, at the endpoints, at the boundary, okay? So Green's theorem is going to do a very similar thing, but with more variables, more. This is in 2D now. Here's Green's theorem. And this is the circulation form. There's another form that we will see in a bit called the flux form. Anyway, let D be an open, simply connected region with a boundary curve C. So remember, open, simply connected. We got a picture down here. Open is does not include its boundary, and simply connected means there's no holes in it, right? And the boundary of the region is the curve C. And this is a piecewise smooth curve. So piecewise smooth means there's finitely many parts of it that are differentiable. They have derivatives, continuous derivatives. Simple closed, so C is a piecewise smooth, simple closed curve. So simple meaning it doesn't cross over itself, closed meaning it starts and ends in the same place, right? There's a lot of adjectives describing what's going on. We have an open, simply connected region and a piecewise smooth, simple closed curve, oriented counterclockwise. Okay, so this is typically the orientation which we would call positively oriented. I think of it as when you're walking around the boundary, the region D is off to your left, right? And off to your right is the outside of the region, right? You're walking along the boundary. The interior is to your left. The exterior is to your right. Okay. Now, if you've got a vector field, P comma Q, and I should point out this is only in 2D here. Green's theorem is just a 2D theorem, not a 3D. Right. So we got a vector field with component functions that have continuous partial derivatives. So P and Q you can take a partial with respect to x, partial with respect to y, and those would be continuous. Right. Then the line integral of f dr along the curve C, and we have this little circle here because C is a closed curve. So this is what they call a circulation integral. So we could write it like this, or we could write it as, sorry, I don't know if you can see my pen here. You can write it like this, and you could write it like this, p dx, the integral p dx plus q dy. Green's theorem says that this is equal to the double integral over the region D of the partial of q with respect to x minus the partial of p with respect to y, dA. Okay. So you're taking, well, you can think of it two ways. From the point of view of like the fundamental theorem of calculus, if you've got a double integral of this function that notice has derivatives involved, this is the partial of q with respect to x minus the partial of p with respect to y. So if you could then figure out what p and q are, then you could evaluate this double integral by doing the line integral along the boundary. Right? That whole double integral can be described by what's happening with the line integral around the boundary. Now, it's not the same functions, right? This is q, this is the partial of q with respect to x, and this is q, and this is the partial of p with respect to y, and this is p. So you have to find those antiderivatives so that you can use them around the boundary. Now, when you're just dealing with one-dimensional things, the boundary is 2 points. Right? But now we've got regions, and the boundary of the region is a curve. Okay? So the proof of this theorem is, I always like when books do this, it's beyond the scope of this book. It does too much. Our textbook does do, in fact, this picture is just pulled right out of the textbook there. They do the case when the region is a rectangle. And they show with a rectangle that this is indeed the case, that this integral is equal to that. Okay. And then they just sort of wave their hand and say, yeah, for general, for more complicated regions, you just cut it up into a bunch of rectangles and it's close enough. It's like, okay, whatever. I don't want to take the time to do the proof. You can read the proof in the book. It's pretty straightforward. Just parameterizes the four sides and evaluates the integral and shows, actually, I think it evaluates this integral and shows that it's equal to that. Anyway. All right, let's take a look at a couple of examples here. I think you'll find that the examples we're doing are not quite the way we use the fundamental theorem of calculus, but let's see here. I've got a curve. R of t is 3 cos t, comma 3 sine t. Oh, I didn't say it, but t is from 0 to 2 pi. So I've got a circle radius 3 centered at the origin, starting at 3, 0, and rotating counterclockwise around. So as I go around, the exterior is to my right and the interior is to my left. So that's positive orientation. And what I want to do is I want to evaluate the line integral around that curve of 2x plus y dx plus x plus 3y squared dy. So I've just chosen a vector field where p is 2x plus y and q is x plus 3y squared. Now, we know how to do line integrals. We could do this. There's no need for Green's theorem on this one. You could just do the line integral. You plug the, you have to take the derivative, right? Find x prime and y prime to substitute for dx and dy there. And then you substitute the x's and the y's in, and you just get an integral dt. You can do that. But I want to apply Green's theorem and see what happens here. Because it tells me, Green's theorem says, I can take the partial of q, the second one over here, with respect to x, and take the partial of p, this first one with respect to y, subtract them, and then just do the double integral over the region. So I'd be doing it over the interior of the circle. And see what happens. Well, the partial of q with respect to x is 1, and the partial of p with respect to y is 1. So the double integral that I'm doing is the integral over d of 0 dA. I can do that. I can do that integral. I don't even have to do any work. The integral of 0 over that region is 0. Okay. Do you notice something here? That this qx minus, q sub x minus p sub y, that is when we were testing for conservative vector fields, we would look at the partial of the first part with respect to y, the first component, partial of the second component with respect to x, and see if they were the same. If they were, and you were on a simply connected region, then you have a conservative vector field, and the line integral on a closed loop in any conservative vector field is 0. And in fact, this is a conservative vector field because qx and py were the same. You subtracted them and you got 0. So if you have a conservative vector field, this is definitely going to be 0 every time, right? Both from the point of view of the line integral that we saw and from the point of view of Green's theorem that you're just going to be doing a double integral of 0. So you get 0 as an output. Right? If it's not a conservative vector field, then this won't be 0 and the integral won't be 0 either. So anyway, there's that. What's the difference here between the way we would use fundamental theorem? I mentioned this, that this is different. That with the fundamental theorem of calculus and the fundamental theorem of line integrals, you're starting with the integral over the whole thing and you're saying what happens on the boundary. In this one, I said, hey, I've got an integral around the boundary and I'm going to look at what happens over the whole thing. It's an equation. You can start with either one and replace it with the other. So sometimes you might be doing a double integral and decide you want to do a line integral instead. Or sometimes you're doing a line integral. It has to be a closed loop line integral, and then you can convert it to the double integral over the region. And in this case, it really behooved us to do the double integral because this was a really easy one. Okay? So this is going to go both ways, although both examples that I'm doing in this video are where I'm starting with the line integral. Okay, the next example. Okay, so my vector field here is xy comma y squared. And I'm going to integrate, I'm going to do a line integral around the boundary of this region here that's bounded by y equals x and y equals x squared. And maybe you can see the little direction arrows that I am thinking of going around this in the positive direction, in the counterclockwise direction, so I'd call that positive orientation. Now, I haven't parameterized this yet, but I'm not going to, because what I'm going to do is I'm going to switch it to a double integral. I mean, I could do, parameterize this curve and then parameterize that curve and then add the two results, right? That when you have a piecewise boundary like this, then you've got to do the individual pieces and then add the results. And that's one of the reasons why I would be inclined to try to use Green's theorem and do the double integral inside, because it's like, do I really want to do all that, do 2 line integrals to get this done? Instead, I can just say the integral around C of f dotted with dr is, well, it's this, right? This is p dx plus q dy, so xy dx plus y squared dy. And now I'm going to use Green's theorem, so I'm going to take the partial of q with respect to x. I got to make sure I do it in the right order, right? And always, yes, it's q with respect to x minus p with respect to y. If I do it in the wrong order, I'm going to get negative the answer I should get. But so Q with respect to x is 0. P with respect to y is just x. So 0 minus x is negative x. So I'm integrating negative x over this region. Well, this is just the calc-free problem, right? This is just the x goes from 0 to 1. And for each x value, y goes from the parabola up to the line. So from x squared up to x. And I can just integrate, doing the y on the inside and x on the outside. So this integrates to negative x times y. Y is being replaced by x and then by x squared right down here. So now I've got the integral from 0 to 1 of minus x squared plus x cubed, which would be x minus x cubed over 3 plus x squared over 4, evaluated between 0 and 1, which turns out to be negative 1/3 plus 1/4, which is negative 1/12. Okay? So again, I'm doing the line integral by doing the double integral instead. So again, backwards. This one, it's more like the easier thing to do is a double integral. Okay? Now, sometimes it's going to be the other way around, and we'll show you some examples of that probably in future videos. Okay? All right, and this is my note. We're doing this backwards. So let's go to another video and try something the other way.